Hello, I'm Sir Conisius or Sir Amos. Today we are going to look at solutions to the non-separable ordinary differential equations of first order. Please, before you watch this video, if you haven't watched a previous lesson that was on steps to solving the either homogeneous equations or steps to solving the non-separable ordinary differential equations, I would advise that you try and watch that video. But that video gives you an introduction and gives you the steps that are involved in solving the non-homogeneous ordinary differential equations of first order. So we want to take an example now on that aspect, and then we see how we can apply the various procedures we learned in our previous lesson to solving some examples. So our first example says that find the solution to y squared minus x squared dx minus 2xy dy to equal to 0. And now add y of 2 to equal to 2. So this is an initial value problem. So to solve this question, what we do is we first of all attempt to make dy dx the subject so that we can put it into the form of the non-separable ordinary differential equation, which we learned to be y prime to equal to f of y over x. So that means we need to make y prime the subject. So we have y squared minus x squared dx minus 2xy dy to equal to 0. So in an attempt to make the y prime or dy dx the subject, I have y squared minus x squared dx to equal to 2xy dy. That is sending the negative 2xy across the equal sign. And so I'll then divide both sides by dx so that I have dy dx at this side. And this will give me y squared minus x squared to be equal to 2xy dy dividing dx. And so I can now divide both sides too by 2xy so that the dy dx stands alone, and therefore I have dy dx to equal to 2 equal to y squared minus x squared dividing 2xy. But we know that y prime is equal to what? Dy dx. So to make our writing very easy, or to make it easy for us to write, we replace dy dx with y prime. And so we have y prime to equal to, and here I will divide y squared by this and divide x squared by the denominator. And so I have y squared dividing 2xy minus x squared dividing 2xy. And then I have y prime to equal to 1. So from here, the y will cancel the y here, leaving y over 2x. So I have y over 2x minus here to the x will cancel, leaving x over 2y. So I have x over 2y. I can then rewrite this as y prime to equal to half of y over x minus half of x over y. So at this point, we have been able to what? To transform the equation into its original form. That is y prime to equal to f of y over x. And so we say that we represent y over x by u. So we say let u to equal to y over x. So that if u is equal to y over x, then making y the subject, we have y to equal to u times x. And differentiating u will give us, differentiating y, that's the derivative of y, will give us u prime x plus u. How did we get this? we got this by applying the product rule. This is the function of u and x multiplying each other. So we apply the product rule and then we differentiate it. So by the product rule, I will differentiate u and then maintain x. Add it to differentiating x and then maintaining u. The derivative of u will give us u prime, while the derivative of x will give us 1. The derivative of u gives us u prime because the u is a function of y over x. So differentiating the u will not give us 1, but rather we have u prime because we have something inside the u. So let's label this one as equation 2, and then we label this one as equation 1. So we label this as equation 1. So we put equation 2 into equation 1. So that is, when we come to this one, we will replace or we will substitute y prime with u prime x plus u. And so equation 1 becomes u prime x plus u to be equal to half of y over x. But y over x was equal to what? U. Y over x was equal to u. So we have, that is here. So we have half of u. Then minus half of x over y. So x over y will give us 1 over u. If y over x is u, then x over y will be 1 over u. And now we apply algebraic manipulations to solve or to separate the variables. So at this point, we have been able to break it down from the non-separable form into the separable form by changing the variable, the dependent variable y. So we now have the function in terms of what? U and x. So we group like terms or we separate the variables. And so we have u prime of x to be equal to half of 2u minus half of what? So okay, so here I can write it as 1 over 2u, then minus u, that is sending the u across. And now we have u prime of x to be equal to u over 2 minus 1 over 2u minus u. So half of u minus u is going to give us negative half of u, then minus 1 over 2u. And so the next thing we do is to apply operations to fractions, that is addition and subtraction of fractions. So we look for the LCM. The LCM for this side is going to be what? 2u. So we use the LCM as 2u, and then we divide 2u by 2 to get u. U times u will give us u squared. 2u times dividing 2u will give us 1. 1 times 1 will give us 1. And so we have u prime of x to be equal to what? Negative u squared minus 1 all over 2u. And so I can group or factorize the negative 1 out. So I have u prime of x to be equal to negative 1 then u squared plus 1 all over 2u, all dividing 2u. So the next thing is to change the u prime. The u prime is the rate of change of u with respect to x. That is du dx. So here becomes x du dx to be equal to negative u squared plus 1 all over 2u. So I have x du to be equal to negative u squared plus 1 all over 2u then dx. So to separate the variables, I have to divide both sides by x, and then I divide both sides by u squared plus 1 all over 2u. So by doing that, I have 1 over u squared plus 1 over 2u, then du to be equal to negative 1 over x, then dx. So this one is one dividing a fraction. So we take the reciprocal. So we have this side to be 2u over u squared plus 1, then du to be equal to negative 1 over x, then x. So we have been able to what? To separate the variables now. So the next step is to take the integral of both sides. So we integrate this side with respect to u, and then we take the integral of this side with respect to x. So from here, the negative can be brought behind the integral sign. And so, the integral of this side, let's state it here correctly. We can use integration by substitution to solve this. But when you also study this one very well, under the derivative of the natural logarithm, ln, we know that if I have, let me say, ln u squared plus 1, and I want to differentiate it, I will differentiate the inner function and divide by the inner function. So the derivative will give me 2u over u squared plus 1. So that means that if I integrate this one, the answers will give me this. So that means that the integral of this is going to be equal to ln u squared plus 1. And then the integral of the 1 over x is going to be equal to negative ln x plus the constant of integration, c. So at this point, we can regroup by bringing the ln x to this side. So, if we bring the negative ln x across the equal sign, we are going to now obtain ln u squared plus 1 plus ln x to be equal to c. But from lots of logarithms, we know that if I have log a base b, if I have log a plus log b, to which both a and b are of the same base, 10, 10, then this is equal to log a times b. By applying that principle, I have a log here added to a log here of the same base. So this will be equal to their multiplication. So I have ln u squared plus 1 times x to be equal to c. And then apply the same laws of logarithms. We know that if I have log a base b to be equal to c, then the a will be equal to the base raised to the power c. So following that, the a is going to be u squared plus 1 times x, that is here, to be equal to the base. The base of the natural logarithm is e, so to be equal to e raised to the power c. To be equal to e raised to the power c. And so, at this point, we have been able to now rewrite it in terms of a solution. So this becomes a solution. But we cannot leave it this way because we have u here, but the question was not given in terms of u. We only introduced the u, so we can bring it back to the original form. We say that, but u was equal to what? Y over x. So substituting u as y over x, I have y squared over x squared plus 1 multiply x to be equal to e raised to the power x. Y squared over x squared, that's the u, y over x, so the square will affect both sides. So therefore, multiply the x across, I have y squared over x plus x to be equal to e raised to the power c. Remember, the x will multiply against this and then it will cancel here, leaving x. Okay, so I will then multiply both sides by x, and the solution becomes y squared plus x squared to be equal to x e raised to the power c. But if we suppose that, supposing e raised to the power c, which is a constant, to also be equal to a constant c, then we have the solution to be, we have y squared plus x squared to be equal to cx is the general solution. So we have this to be our general solution. But the question was given as an initial value problem. So we need a particular solution. So we apply these values. But at y1 to be equal to 2, it means that x is going to be 1 and y is going to be 2. So putting these values into the general solution, we can obtain the value for c. And so we have 2 squared plus 1 squared to be equal to c times 1. And we have 4 plus 1 to be equal to c. So therefore, c will be equal to 5. So if we put c as 5 back into the general solution, our particular solution becomes what? So we have hence, we have y squared plus x squared to be equal to 5x. The c is 5. Is the particular solution. So dear viewers, this is basically how non-separable ordinary differential equations are solved. Now, this becomes our particular solution and this becomes our general solution. Now, when you also study the constant, this constant is also an exact differential equation. So we can apply the exact method to solve it as well. But for now, we solve it using the non-separable approach. So, watch or go to my YouTube channel. You can visit my YouTube handle, Obukanisa Tutorials, for more examples and solutions. Please subscribe to my YouTube channel, watch, share, and like. And please follow me to watch or to have more experience in ordinary differential equations. Thank you.